Or you want
me now?
Yeah.
Oh, okay.
It's okay now.
So, how many still suffering with form of 9? So, not to mention form of 11. Okay. Well, I don't know why EM and GIPS is troubling you. Maybe just because the modeling of homework is not so easy to find on Google, I guess. But basically, EM itself is just a general algorithm. It's not specific to any model. And yes, what makes it difficult maybe just because the prediction model that Menzo put on homework 9 is a little bit involved. Yeah, it maybe takes you more time to do the factorization other than making up the EM itself. Okay, I'm going to first introduce EM. Oh, if you can hear me, just raise your hand. I'm going to first introduce EM under the context of Gaussian mixture model. Then if we still have time, I'll try to go through some basics of group sampling, but I don't think I'm going to be able to cover that much in groups. I'm not a pro at that. In terms of homework, yeah, the method will be clear afterwards, so we'll be able to reach him and ask him some homework specific questions. Okay, let me see if it's really focused. Okay. So, did Alex cover Gaussian mixture modeling in class, by the way? Yes.
Very briefly.
Yeah, I recall he mentioned, but not into details. But I assume most of you know what it is about, right? So when you have a mixture of distributions, this is what. So you want a mixture of Gaussians to represent the distribution of the occurrences or of certain data. But the thing is that you do not know which Gaussian or what portions of Gaussians that each occurrence may be associated with. That's why we call it a latent variable, usually denoted in C. So, by the way, for each of the Gaussian, the parameters are simply the mean, mu j, and covariance sigma j. And we also need the mixture weight, which we denote here as pi. So suppose we have 3 mixtures, so k is equal to 3, which is the number of mixtures. And our data is denoted by D, which is a collection of observations. Suppose there are n of them. So now we introduce the hidden variable, or sometimes they call hidden data, which is simply C equals to C1, C2, Ck, here k equals to 3. So these are our setups, and we write the data likelihood like in this way. So now that we have introduced the hidden variables, so we need to aggregate the likelihood over all hidden variables. So you get something like this.
So should there be n hidden variables, one for each x?
No, there are k hidden variables here. C equals to 1 to k. So this is C1, this is C2, this is C3. C corresponds to these Gaussians. The C is not the Gaussian itself, but corresponds to the Gaussians. So you can think of that, and the occurrence of each data, they follow a distribution, which is a mixture of the three distributions here.
So I mean, in homework 9, there are n latent variables and n random variables.
Yeah.
Right?
Yeah.
I think it makes sense because for each x, you have to know from which mixture it comes. So you need one latent variable per x.
So pretty much an n by k
The domain
matrix.
of each CI is k possibly values, right? You
Yeah,
have
that's
n
it.
variables, but each has a domain of size k.
That's. I think that's a good way of looking at it. Maybe notation here is a little bit messy here, but C is often referred to as the hidden data, or sometimes hidden variable. And I'd like you to look at this picture here. So you can see that the data likelihood is often in some way like this. They're sometimes in most cases they're not convex. That you cannot find the element. What they're drawing here are simply what EM is trying to do. Every time it's trying to find a lower bound, a very tight lower bound actually, of the data likelihood, and then we try to identify this point where they are equal. And notice that these curves here, they're convex. So in that case, we can always find the output point, and then we can go all the way to the local optimal, but it's just local. Then there's no guarantee to be global. If your likelihood function is like this, then EM cannot get you to the global optimal point. Now then we have written the data likelihood like this. So if we expand it, it's simply going to be like this. And notice that where we have Gaussians here, so this corresponds to Gaussian, and this is simply the mixture rate. So they become this. So this is the data likelihood, which is pretty simple. Yes.
Do you have the sum over z in front also?
Oh, these are the same actually. Just C. Okay, C consists of C1, C2, and CK. I'm just using k equal to 1, 2, but this is supposed to be 3. But yeah, the k equal to 3 in that case. Yeah.
So when you write Z1, 2, 3, this is actually the very latent.
Yes, the latent data.
Latent data. Right?
Yeah. So
If you write 1 to k instead of Z1 to zk.
yeah, they're
Just
the same. They're the same. They are both referring to the latent variable.
The latent. It's the value of the variable. 1 to k.
Well, it's not the value actually. They're just a variable. They're there in order to. The variable there are simply indicating which Gaussian that it corresponds to, such that we can write things in this way. So do not struggle with what exactly the value is, because it's not going to be very meaningful here. So now we have the likelihood. We can have the log likelihood, of course. By writing this way, then we can simply have. Yeah, for simplicity, I'm just writing this C here, and you know that we're iterating through all the latent variable. So this corresponding to the log of this. And now we're going to do a little bit trick here. We're going to multiply a QZ and also divide it by a QZ. And I'll introduce in a moment why we're doing this. And because you saw that they're not necessarily convex, that they can be arbitrary. So what we're trying to do is we're trying to locate these approximations, or to say these curves, to get a picture of a partial picture of the curve actually. So what is going to happen if we do that is by introducing this QZ, we can regard this part as maybe as a dummy function. Let's call it capital QZ. And then this becomes essentially a log of an expectation of this capital QZ. So it's going to be we're simply taking the expectation over QZ of capital Q of this capital QZ. So these two are equivalent. We're simply adding something, dividing something. We're just looking at this formula in a different way, and later we'll do some tricks on it such that we can get some curves that I just showed you. Okay, did Alex introduce Jensen's inequality in class? Ever heard about Jensen's inequality? Okay. All right. Don't bother then. There is an inequality called Jensen's. It says that f dx is greater than or equal to e, the expectation of fx. Now consider this formula here. We can follow the Jensen's inequality, then we can write out something like log e over q.
So, but this is only true for concave functions, I think.
What?
You have to say what f is.
What?
Because Jensen, the sign will flip when you have a convex function.
Oh yeah, you're right. Good catch. But here this is true.
What else?
What?
Is that convex or concave?
I believe that's convex, but it turns out to be not. It's just a matter of adding a negative sign, right?
This inequality is, at the time this inequality is true for concave, and you want to set fx as log x, right?
Say again?
Here fx is log x, right? No?
Fx is
log function.
okay. Yeah. Here fx is the log function.
Yeah, and log is concave.
It should be concave. That's for concave. The inequality.
Yeah, you're right, I think. So we have this, I need to look at that. I actually forgot the direction of the inequality.
It's less than or equal to. It's the other way.
Yeah.
Look at Wikipedia.
Okay. Now that notice that we're trying to take points like this, and we want the inequality to be an equality. So yeah, so we're trying to see if this can be an equality, and that depends on how QC is formulated. So yeah, that's why I was not paying much attention to the direction, because my goal is to trying to get the point of inequality, and that makes things actually turn out to work very beautifully. So it turns out that if we want this to be an equality, then QZ is equal to PZ given X. Right? Then we can simply prove it. We can write that E over Q log P XZ. Suppose Q is PZ given X. Then we can prove it all the way like this. Right? Then we can move it like then you can see that this is actually 1. Does it make sense? Let me see if I missed stuff here. Yeah, this is simply what we got here actually. Then you can see that if Q is equal to PC given X, then I'm having to return to the very beginning. So then you know that when QZ is equal to PC given X, the equality closes. So that's a very short proof.
And that should be larger or equals to, because that is a lower bound. Because log is a counter function, we are doing JSON.
Yeah, I understand. It's just a matter of adding a negative sign before that, or if it turns out that you're going the other direction, just add or remove a negative sign. That always works.
And then in the writing there, the larger or equals to should be correct with the smaller. That should be larger or equals.
Okay. Yeah. Yeah, I was looking at an old lecture note I took like 1 year ago. So yeah, maybe I didn't pay much attention to the reference. Now that you know that the function can be. Now that you know that QC should be equal to PC given X, that gives us the equality. And then we actually get a tightened lower bound. Okay, continue from here. So previously we left Q, capital QC equal to this quantity. Now we're just rewriting it. So this thing is a constant. Of course, we're simply taking the estimation of this thing itself. So it's constant can be ignored if we're taking argmax. And the remaining part we can write out like this, based on our observation of rule above. So this simply QC. Okay, the main line here, so I don't want to miss running all of these. So it's like this. So this is simply counting all the data points, and since we're taking log of them, so we're doing summation instead of taking the products, and we're extending these two terms here. So recall that the P C given X it is what we got in previously QC, and this term is simply this, and so that P X given CK is simply the probability that X belongs to one of the latent variables, and then what is the probability that it occurs, and that P secant K is simply the mixture, which is simply type A. Now we can write out the equation of normal distribution here, so it's just very lengthy. So yeah, from here to here, and not including this. So like this, and then to make them a little bit clear. So we're taking the log of this term inside this bracket. Then we get this. So we're simply getting them out of this log sign. So we get rid of this exponential sign. Then we get something like this. There are summations. Then remember to take the log of the mixture weights. And then we go here. We're simply rewriting it. This is just a matter of simple back here, and these remains the same. So yeah, and this becomes our objective. Now that we have reduced the objective of the entire multiplying function into one of these curves, into the curves actually, not one of these. So this will become any of the curves as we perform the EM. Now a little bit comment on the M steps and E steps of EM. So what will happen is that this weight will be estimated in the E step, and this will be estimated in the maximization step. Now this becomes a problem of finding better parameters of the model, which are simply the mu k, the sigma, and the mixture weight k from which is 3 in our case. So what we do is actually pretty straightforward. It's simply simply infinite while loop. When it's not converged, so we do the E step to find the expectation of so what do I mean by the complete data? So this includes the what do I mean by the complete data? This includes both X and hypothetical unobserved hidden data C. So to get this, we need to find the P, Z, K given Z given X, which K. Then we take MLE. So this one can be easily estimated using MLE. The formula is like this. Which is simply notice that in the E step, we're fixing the parameter of the Gaussians. So we are assuming that the mu and the sigma are known, are constants, so that we can use it in the MLE. So there goes the E step. And then for the M step is actually more straightforward. It's just using the PZ given X, the little QZ essentially to estimate the mu K and the sigma K. And which is basically focusing on this term here. So in E step we're doing this, and in M step we're doing this. And what we do is to simply let me write out this very long thing, which is simply to the argmax of mu K and the X and the sigma K. Yes.
So this is the case without priors, right? On pi,
Without priors?
on pi and theta.
So you're sort of given pi k, your pi k is sort of fixed, or
Yeah.
as well as your mu and the covariance matrix.
In M step, the mu and the covariance matrix are not, but in the E
Yeah,
step they are fixed.
Yeah, but they are not dependent on any priors, which is the case in the homework.
So in the homework, the difficulty was that we had these priors that we didn't really know how to incorporate. We were supposed to do MAP instead of MLE.
But
That was
in that case, you should do MAP instead of MLE.
Yeah, so that was, I think most of us understood the MLE thing, but not the MAP, or how to go from the MAP derivation to what you just presented.
But MAP is just a matter of, so do you have so are you provided with the prior or you need to estimate it?
Yeah, we have the prior.
Okay, but let's just wish that answer will be here very soon. our recording to give an explanation on that. But since you know NLE pretty well, then I'll just cut you the point. So the M set is simply taking the argmax over that lengthy term. And this, as I said, is fixed. And this term, as it's not related to mu or sigma, so this gets ignored. And it's just a matter of taking derivatives. And yeah, by taking derivatives over mu k, you get something like this. It requires a little bit of tricks here. The trick is that the absolute of this capital A here is to this, such that you can go from here to here, and you can do the derivatives and reduce this thing to this. And this, there is a formula that gets you from here to here. And starting to 0, then you can get the closed form solution of sigma k. So that pretty much is what the M set and E set and how the squares of